Hi guys, welcome back to my channel. Today we are going to be having a look at vector resolutes. Previously we have examined the scalar resolute of B onto A, and we used the term shadow to describe what was happening here. So if we were to imagine a torch that's shining down from B, what is the length of that shadow along A? In other words, what is the length of this particular line along here? So this is given as a single value and is the magnitude of the line OA. And we found this previously using this equation where the projection of B onto A, so in other words, the shadow caused by B on A, is given by the unit vector for A, which is acting in this direction, multiplied by our vector B. Now, what if we weren't actually interested in finding out the length of the line, and rather we were actually interested in finding the vector that this line makes, so the vector going from O to A? Well, this is now called the vector resolute. There are actually two different components here that we can examine with the vector resolutes. So, of course, the most logical, or the first vector that we can look at, is this vector here that's going from O to A. So this vector is parallel to my original vector A. We can also examine this vector here that's going from A up to the tip of this vector B here, and that vector is acting in a perpendicular direction to A. So we're going to call this parallel vector the vector B with these two lines, because these two lines are used to represent a vector that is parallel. And this vector here that is perpendicular, we are going to use the symbol with the B and perpendicular angle, because this represents that this is coming straight up from this vector A here. So how to actually go about finding these two vectors? So if we know the length of this line here, and we can calculate using the projection of B onto A is equal to the unit vector A times by B. So we find that length of that line along there, and we multiply it by the unit vector acting in that same direction. And so that's going to give us this formula here, where that's going to be equal to our value that is parallel to that value A, or parallel to the vector A, I should say. Now, if we wanted to find the perpendicular vector, so since the parallel vector is acting in this direction and the perpendicular vector is acting in that direction, that wasn't a great line, sorry about that, then what we can do, if we wanted to find this vector here, B, that's going to be the resultant vector of this vector and this vector. So in other words, if I was to take the parallel vector plus the perpendicular vector, that's going to be equal back to my original vector. And so if I rearrange this formula, I can get the perpendicular vector is equal to the original vector, take away the parallel vector. So just a little bit of simple algebra there. Last thing I'm going to do is I'm going to replace this now, since we know that this value here is equal to this, and that's how I end up with my final formula here. So let's go ahead and let's use an example showing how to calculate the parallel and perpendicular vector resolutes for our shadow of our projection of B onto A. Here we have our example where A is equal to negative 2i plus 3j. So in other words, this vector acting in this direction here. We also have the vector B is equal to 4i plus 2j, which is going to be the vector acting here. The first thing we need to find is the scalar resolute of B onto A. So if we were to imagine a torch and our torch was shining a light in this direction, what would be the shadow from B onto A? Now, I'm sure you can appreciate here that A doesn't actually lie below B. A is actually all the way over here. And so this length of this line may actually end up being a negative value because it's acting in the opposite direction to our vector A. So let's use our formula and let's calculate this length here. The projection, or the shadow of B onto A, is going to be given by the unit vector for A multiplied by our vector B. So to find our unit vector A, remembering that the unit vector is the vector that's acting in the same direction as A, but only has a magnitude or a length of 1. So in other words, this vector about here. So we're going to find the magnitude of our original vector first, and then we're going to divide through by that value. The magnitude of our vector A is given by the square root of x squared plus y squared. So for us, that's going to be equal to negative 2 squared plus 3 squared. Negative 2 squared is 4, 3 squared is 9, so our value is going to be equal to the square root of 13. So the length of this line here is going to be equal to the square root of 13. To find a vector that's only going to have a magnitude of 1, we're going to divide through that original vector by the square root of 13. So that's going to give us negative 2 over root 13i plus 3 over root 13j. So this is equal to our unit vector for A. Now we can substitute this back into our shadow formula or our projection formula. Since this is already in component form, we're going to find the multiple of the x components and add that to the multiple of the y components. The length of our line is going to be equal to negative 2 over root 13. So again, the reason that this is negative is because this shadow is acting in the opposite direction to our vector A. And we kind of thought that was going to be the case, because if we were to imagine our torch coming from here and the shadow coming down here, or the light source I should say coming down here, it makes sense that that shadow is acting in the opposite direction. For B, we're going to be finding the vector resolute that's parallel to A. So to do that, we're going to use the length of the line that we just calculated, which was negative 2 over the square root of 13, and we're going to multiply that by the vector A. Now, because this is negative, it is acting in the opposite direction, and so it will switch the position or switch the direction of that vector. So remembering that formula, when our vector or our projection is parallel, we're going to use these parallel symbols. That's going to be equal to A dot B multiplied by our unit vector, which is kind of intuitive, I think, at this point. So that's going to be equal to negative 2 over root 13 multiplied by our unit vector A, which was negative 2 over root 13i plus 3 over root 13j. So that was from the previous question. So this is going to end up as 4 over 13i minus 6 over 13j. So in component form, this does seem to make sense since this is positive x, negative y. So this point here, or the direction of this vector here, is going to be 4 over 13i minus 6 over 13j. Our last step is we are going to find this vector here that is perpendicular to A. So we've now found this vector here, so I'm going to write that down. I also have the original vector for B. And so what we can find, if I was to have just this vector here, that's the resultant vector of this. So that's going to be equal to the parallel vector plus the perpendicular vector here. Now, we have this information here, we have this information here, and so rearranging this formula, we are going to get that the perpendicular vector is equal to my original vector minus the parallel vector. Now, my original vector was 4i plus 2j, and my parallel vector, which I just determined, was 4 over 13i minus 6 over 13j. So to complete this, I'm just going to equate the two horizontal components and the two vertical components. So the final vector that we get for our perpendicular vector is equal to 3 and 9 over 13i plus 2 and 6 over 13j. So just to simplify that a little bit, that's going to become 48 over 13i plus 32 over 13j. So that's how we use the scalar resolute to find the vector resolutes for both the perpendicular and parallel components of a vector. All right, guys, I'll see you in the next video.